Welcome, everybody. I want to take a look at a couple of problems with you today, mainly related to the limit kind of questions that we've been working on in class. I want to get several examples in front of you this morning. So we'll go ahead and start with this first one. If you haven't logged into Learning Catalytics, go ahead and do so. Here, I want you to find the limit of this function, and we're going to use algebra and limit laws to do that. I will give you a hint to get started on this function, and that is, obviously you should plug in t equals 0 to see if it'll directly substitute, which it won't. We'll talk about that in a second. But go ahead and try to work this by finding a common denominator. So get a common denominator there and combine those two fractions and see if you can find the limit. I'll give us about 3 minutes, and then I will start to look at it and see where we are. All right, as you continue to work on that, let me talk about why direct substitution fails here. If you directly substitute in the limit t equal to 0 to both pieces, you'll get 1 over 0 minus 1 over 0. If you place a very, very small number in the bottom of a fraction, the fraction gets bigger. So as the number here tends towards 0 on the bottom, this fraction becomes infinitely large. So you get infinity minus infinity. I know you're tempted to say infinity minus infinity is 0. It is not necessarily 0. It could be anything. Think of this as a race between two things that are running to infinity. If both objects run at the exact same speed, then the distance between them is constant. If one runs much faster than the other, the distance between them becomes infinitely large. So the point is, this is another indeterminate form like 0 over 0 is. This does not tell us anything. So we're going to have to use some algebra to try and handle this. So what you should be doing to finish out this problem is getting a common denominator. All right, I'll give you about another minute to finish up and enter an answer, and then we'll take a look at it. All right. So here are the results. 40% of y'all correctly did it. The correct answer here is 1. Let's take a look at it. So once we start this process, getting a common denominator, the easiest way to do common denominators is to look and see what factor is missing and then multiply by that. So if you look at t squared plus t, that's t times t plus 1. So you see that it has the factor of t that this one has already, but it's missing, this one's missing the t plus 1. So the common denominator here would be t plus 1 over t times t plus 1 minus, this one already has the full denominator. So if we combine those, you'll get the numerator there, t plus 1 minus 1, so that'll just be t in the top. And then the bottom will be t plus 1. Okay, once you do that, remember the goal of algebra in all these problems is to algebraically manipulate it to a point where you get a cancellation to occur. And after that cancellation occurs, reevaluate the limit. So we can see here that you have t divided by t, which is where the cancellation is going to occur. And so that'll leave you, the limit as t goes to 0 of 1 over t plus 1. And so if you evaluate, if you do a direct substitution there and evaluated t equal to 0, you get 1 over 0 plus 1, or 1, which was the correct answer. So if you ever see a limit of two fractions that are added or subtracted, and you're getting an indeterminate form to start, you should try getting a common denominator. That's the typical trick that's used for these kinds of limit problems. All right, let's try another one. All right, so this next one I'm probably going to have to say a little bit about before you jump into it. So go ahead and get it sort of copied down, ready to look at. And then I want to talk us through something before I just let you go on this one. All right. So here is the limit problem we're looking at. And if you directly substitute in -4, let's check that. You should always check that first because I may be actually giving you a very easy problem where it does directly substitute, but so you always need to check that first. If I plug -4 in, I get the square root of 16 plus 9 minus 5 over -4 plus 4. 16 plus 9 is 25, so that's the square root of 25, which is 5 over 0. So we get 0 over 0, and we know from class that that is indeterminate. Now, what I wanted to talk about here is something that you may or may not know. It's something called a conjugate. So if you look at something that's of the form like the numerator is here, so if we look at this numerator, it's of the form square root of a minus b. The conjugate of that is the square root of a plus b. So if you this is the conjugate here. If you multiply a term by its conjugate, something very nice happens. The square root cancels. So you can see here, if you FOIL this out, square root of a times square root of a is the square root of a squared, which is just a. The inside term and the outside term, because this is a difference of squares here, the inside term and the outside term cancel, and then you get the last term, which is minus b squared, so you get a minus b squared. Basically, the way to remember this rule is if you multiply something by its conjugate, then you square the first term, you square the last term and you subtract the two. So the square of the first term, square of the last term, and subtract the two. So what I want you to do here is multiply this expression by its conjugate and then see what cancels and work the limit from there. I'll go ahead and do the first step with you, and then I'll let you finish it out. So the conjugate of that numerator would be the square root plus 5 instead of minus 5. So that's its conjugate. All right, so all I've done here algebraically is multiplied by the same thing on top as bottom. So I've multiplied by 1. I haven't changed the limit at all. But now algebraically, I should be able to simplify what remains. My advice to you is when you do this, do not distribute this x plus 4 into this term. Leave these two terms separate on the bottom, and then just evaluate it after you get a cancellation. All right, I'll let you work on that for a little bit, and then we'll see where we are. If you have any questions, feel free to ask.
Do you want us to simplify the answer?
Learning Catalytics will get it as long as, like, if you put in 2/4 or 1/2, it'll know that they're the same. But in reality, yeah, if it's easy to simplify, you should simplify.
So keep it in fraction form or keep it in decimal form, doesn't matter.
It will take either. But I think fraction's easier here because if you do the work, it results in a fraction. All right, almost all of you have responded. I'll give us about 20 seconds here to finish it out.
Professor, on the test, will we be able to use Desmos to kind of verify our answer, or
Yeah, absolutely. But on a problem like this, where it says use algebra, I'll expect you to show the algebraic steps.
okay?
So yeah, Desmos can't be a replacement for doing the work, but yeah, I would encourage you to use it to check yourself. If you have time. That's the kind of thing that can slow you down on the test. But if you have time to go back and check some stuff, yeah, it's definitely useful. All right, so what we have here, y'all did pretty well on this one. This one's a little difficult. 60% of us got it correct, and this one's pretty close. I think I just missed a factor there. So not bad. All right, so let's take a look at it, finish it out together. So if you look at the multiplication that occurs in the numerator, I'm just following this conjugate rule, which says you square the first term. So the first term is a square root, so the square root disappears. And then you square the second term, 5 squared is 25, and then you subtract the 2. So that's your new numerator. And then the denominator, I can't forget my limit sign here. The new denominator is just going to be x plus 4 times that conjugate. So like I said, don't try and put those together, leave them separate, because you're just going to evaluate it here in a bit. All right, we're looking for a cancellation to occur. So I'm going to simplify the numerator a little bit more. You've got 9 minus 25 is negative 16. And then x squared minus 16 is a difference of squares, which factors into x plus 4, x minus 4. And so here is where you get your cancellation. X plus 4 cancels. And then what's left, I'm going to directly substitute into, since I have a cancellation now. So plugging in negative 4, I get negative 4 minus 4 in the top. If I plug negative 4 in here, it's 16 plus 9, square root of that is 5. So I get 5 plus 5 in the bottom, which gives me negative 8/10, or reduced negative 4/5. So the moral of this problem is you should be on the lookout for using conjugates anytime part of your limit problem contains a square root term like this. So in particular, we could do like, different conjugate forms. Square root of A plus B, its conjugate would be square root of A minus B. You could have both terms with square roots. So you could have something that looks like this, in which case its conjugate would be square root of A minus the square root of B. So this works in both directions. You could have it on the second term instead, in which case the conjugate would be this. So looking for these kinds of things in your problem, if your limit has these sorts of things in it, then this conjugate method is the method that you would want to use. All right, let's look at another problem. All right, so on this problem, you have a piecewise defined function. You have the function x squared plus 1 for x less than 1, and then you have the function x minus 2 squared for x greater than or equal to 1. So the only question that I'm asking you here is, and I'm not asking you for the value of the limit, I'm just simply asking you, does the limit at 1 exist? So the limit at 1 would be well, I don't want to give it away. basically you change over at 1, right? So you've got the function on the left and you've got a different function on the right, and they change over at 1. And so we have to figure out whether or not this limit exists at 1. All right, this should not take very long, so I'll give us about a minute here, and then we'll see where we're at and go from there. All right, all of you have responded. So 75% of you think no and 25% yes. So the correct answer there is no, it doesn't exist. Let's take a look at why. So the problem that you have there is because it's piecewise defined, you have to check the limit from the left and the limit from the right and make sure they're the same. So your function here is x squared plus 1 for x less than 1, and x minus 2 squared for x greater than or equal to 1. I want to show you in Desmos how you can plot piecewise functions. All right, so if we open up a Desmos tab here, the function that we're looking at is x squared plus 1. So I'll say g of x is x squared plus 1, but we're limiting its domain to x less than 1. So you can see the first function there, the little curly braces out to the side limits the domain. So what Desmos will do is it'll draw in the correct function, x squared plus 1, but it'll only do it for x less than 1. And I'll name h of x the other function here. And it is x minus 2 squared. And once again, this is for x greater than or equal to. If you're looking for a greater than or equal to symbol, you can bring up the little keypad here at the bottom, and it's got all the less than, greater than symbols. So x greater than or equal to 1 would be the correct one here. So you can see that this is the graph that we're being asked the limit question about. We know that this circle is filled in. So we know that the point at 1, h of 1 is filled in. And then the other point at 1, g of 1, that is an open circle because it doesn't include the point at 1. It's not giving me that value. So what is it, 1, 2? Yeah. So the point at 1, 2, that's an open circle. So this is the piecewise function that's being defined here. And you could do this graphically if you want to. Look at the limit from the left. The limit from the left is 2. And look at the limit from the right. The limit from the right is 1. Because the two limits are different, then we say that the limit at 1 doesn't exist. But I want to talk about how you would do this without ever looking at a Desmos graph. All right, so let me move away from that for a second. So here we have the problem, and we know that the break point is 1. So this breaks over at x equal to 1, which means that I should look at the limit as x approaches 1 from the right. Well, what function is defined to the right of 1? Well, x greater than 1 is the right of 1. So I should look at this function to the right of 1. And I should look at this function, the other function, to the left of 1. And so all I'm going to do is calculate those two limits. Those limits are not difficult to calculate because you can both directly substitute in. So if I plug 1 into this limit, then I get 1 minus 2, which is -1. -1 squared is 1. If I plug 1 into this limit, I get 1 squared plus 1 is 2. Those two limits are not equal to each other. So since the limit from the left and the limit from the right don't match, based on our limit law from Monday, we say the limit at x equal 1 doesn't exist. So since the limit as x approaches 1 from the right does not equal the limit as x approaches 1 from the left, then the limit as x approaches 1 from both sides simultaneously does not exist. So you should always be wary of any place where you switch functions in a piecewise defined function about the limit existing. The only way that the limit can exist is if the function value is in agreement at 1. So you test the function value in here, you test the function value in here, and you make sure that they agree. All right, let's try another problem. All right, how do we handle absolute values? I put this problem in here specifically because I wasn't sure that we remembered how the absolute value function is defined. I know you know how to use it. For instance, if I said, what's the absolute value of -9, you would tell me 9. But I wasn't sure we remembered how it was defined as a function. So I wanted to go over that with you. So let's take a look at that together real quick. If you talk about absolute value function, it's defined as being a piecewise function. You get x back if x is greater than or equal to 0. But you get the opposite of x back if x is negative. So in other words, if x is -9, then you get -9 or +9 back. I think a lot of us know what the graph here looks like. It's this sort of classic V shape. So this is the graph of the absolute value function. And so what this means for us is if we're working any limit problems like the one that's being asked here, so our example is to calculate the limit as x goes to -6 of 2x plus 12 over the absolute value of x plus 6. If we're asked to calculate a limit of this type, then whatever value makes the absolute value 0, here the value of absolute value of x is 0 at 0, but here it's 0 at -6, right? So the denominator is 0. And if you directly substitute in, you can see if you plug -6 into the top and you plug -6 into the bottom, you get 0 over 0. So because it's an absolute value, I have a different function to the left of the breakpoint than I do to the right of the breakpoint. Now, they probably agree at the breakpoint, but you still have to check it because it's part of a larger function here. If I were just talking about the absolute value itself, then it would just be 0. But because it's in the denominator of this other fraction, I have to look at this thing from both the left and the right. So if I look at it from the left, what function should I write down here? Does anybody want to chime in on that? What does this function look like to the left of -6?
Would it be -2x plus 12 or -2x minus 12?
Well, you get 2x plus 12. The only thing that changes to the left of -6 is the absolute value. So numbers to the left of the breakpoint. So for instance, pick a number to the left of -6, like -7, right? So if you were to plug in -7, the thing inside the absolute value would be negative. And if you have negative values inside the absolute value, you take the negative of them. So values to the left of -6 are negative, so the absolute value is the negative of those values.
Okay, that makes sense.
Similarly, if you were to look at values to the right of -6, if you plug in values to the right of -6, say -5 or 0 or 1 or whatever, all those values make the absolute value positive, and the absolute value for positive values is just whatever's inside the absolute value. You don't have to negate it. So here, this would be 2x plus 12 over positive x plus 6. All right, I want you to finish it up from there and tell me which of the answer choices is correct. I'll give you about another 30 seconds. It shouldn't take you very long to close this one out. All right. Just about everybody has responded. Good, we're all in. So the correct answer here is E, does not exist. 75% of you, that's good, figured that out. Let's take a look at finishing it out ourselves. You can see here in the numerator that we can factor out a 2, which will then cancel with the factor of x plus 6 in the bottom, leaving us with 2 divided by -1, which is a constant, and the limit of a constant is the constant. So here you get -2 for the limit. Same thing down here, except you don't have the negative running around. So when those cancel, you're left with just 2. So you should treat this very much like the piecewise function before. You have a different function to the left of -6 than you do the right of -6. So in terms of calculating the limit, you have a different limit from the left than you do from the right. And so because these two are not equal to each other, the limit as x approaches -6 from both sides, the full limit here of the original problem, that limit does not exist. So the moral of this story is anytime you're asked to work a limit problem involving an absolute value, because the absolute value function itself is a piecewise function, you're always going to have to do a limit from the left and a limit from the right, assuming that direct substitution doesn't work. You should always do direct substitution first, plug the -6 in, make sure that it's not going to work before you do this next step. But if the direct substitution does not give you a credible answer, then you have to treat it like a piecewise function example where you look at the limit from the left and the limit from the right and compare them. Remember, if you're to the left of the point, you add a negative to what's inside the absolute value. And if you're to the right of the point, then you just drop the absolute value signs and leave it positive. All right. Let's look at another example. All right, so we've already touched on how to do one like this. So I shouldn't need to tell you anything here. I'll just let you go and see what you come up with. All right, you got about 30 seconds to finish it out. All right. So here are the results. 1/6 is the correct answer. 64% of us got that. That's not too bad. These conjugate problems can be a little tricky. So let's take a look at it. I mentioned just a second ago, this is a conjugate problem. So we know that, well, first we should directly substitute to check. So I'm going to go ahead and do that. And if I directly substitute, I get 3 minus the square root of 9 over 9 minus 9. Square root of 9 is 3. So this is indeterminate. So I'm going to use the conjugate method that we used earlier by taking the limit And the square root term is in the numerator. So I'm going to multiply the numerator and the denominator by the conjugate of that term. The conjugate is, since this is of the form a minus square root b, the conjugate is of the form a plus square root b. And so if you multiply through, you square the first term, which is 3 squared is 9. Square root of t squared is t, and you subtract the 2. So the numerator is 9 minus t. And then do not combine the denominator, leave it separate so that you can see the cancellation. And you'll see that that piece right here cancels with the piece we have there. So you're left with 1 over 3 plus square root t. And anytime you have a cancellation that occurs algebraically, you should redo direct substitution. So if I directly substitute in here, I get 1 over 3 plus square root 9, which is 1 over 3 plus 3, or 1/6. So 1/6 is the correct answer there. Pretty encouraged because it looks like 64%, and then somebody got 1/18, which I suspect was just a little bit of a small error there. So 73% of the class looked like they were using the right technique there. All right, let's do, I think we got time for one more. All right, so go ahead and give this one a try. I'm not going to say anything about it. I'm just going to let you go. I'll give you about 2 minutes, and then we'll kind of see how everybody did. All right, you got about 20 seconds. All right, everybody has answered. So all the results are in, and not bad, guys. Not bad. You did really well. 66%, 67% of the class got that correct. The answer is 3/2. Let me just show it for you. You can kind of see it there on your screen, but I want to talk through it a little bit. You should always check direct substitution first. I've been doing that on every problem. It can save you some time. If you directly substitute into this, first off, using limit laws here, the limit comes inside of the square root. So I can bring the limit inside the square root. And at this point, I'm kind of forgetting that that square root's there. I'll just kind of leave it off to the side till I'm done taking the limit. If I look at the things that are inside the square root, it's just a rational function. And we know that rational functions have the direct substitution property as long as their denominators aren't 0. So if you plug 2 into this function, you can immediately see that the denominator is not 0. So I know I'm not going to have to do any fancy algebra here, that this is going to directly substitute. So if I plug in 2, I will get, let's see, 2 squared is 4, 4 times 2 is 8, 8 plus 1 is 9, divided by 6 minus 2 is 4. So the square root of 9 is 3, the square root of 4 is 2. So 3/2 is your answer. So this example is a good one to finish up on because it just reinforces the point that you should always check and make sure that your limit can't be directly substituted into. That's always the first step on these limit problems. All right, if y'all have any questions, we've got about 3 minutes left before 8:50. But if not, have a good weekend. I'll see y'all soon. Yes, you're allowed to use Desmos for the skills quiz. Yes.
And you said we need to have the skill quiz printed out and ready for Monday?
Yeah, you don't necessarily have to print it out. If you want to do it on your iPad, you can just bring your iPad with you. You just need to be able to be in a position where it's finished so that you can grade it when we go over it.
Yes, sir.
Are we getting extra credit points for attending Friday Learning Analytics? Is that kind of what you said at the beginning of class?
Yeah. Yeah, so all these problems that you're answering, you're getting bonus points for. I won't add them up until the end of the year, but yeah, you're earning bonus credit for even the ones in class. Like if you answer the Learning Catalytics questions in class, if you have an account set up for it, then you're earning bonus points.
I have a question. I'm like, I don't know why, I'm really struggling with like velocity equations and stuff. Would you be able to just give me an example of that to know how to set it up and what to substitute where?
Are you talking about for like finding average velocity and instantaneous velocity and that kind of thing?
Yeah, so like number 1 and 2 on the homework.
Okay. Let me see if I can bring the homework up real quick.
I'm pretty sure, like I know, I feel like I can, like I conceptually know how to do it. I just don't know how to get started, really.
So number 1's it's talking about a cardiac monitor used to measure heart rate.
Yeah.
Okay. So it says use data to estimate the heart rate after 40 minutes using the secant line, right? So secant line, excuse me. So secant line slope is just your regular slope formula. In this case, it would be the change in heart rate divided by the change in time, right? So, but the A says between 36 and 42, right?
Yeah.
Okay, so your time change is 42 minus 36. And then if you look at the heart rates that are associated with that, associated with 42 is 2942. And associated with 36 is 2533. So whatever that number is, that's your I think it's what, 68.2?
And that's just the answer for that one?
Well, yeah, it's it says the monitor estimates its value by calculating the slope of a secant line. So the slope of a secant line is just slope formula from high school. It's the change in It's the change in the y values divided by the change in the x values.
Yeah, okay. I just keep overthinking these.
Yeah, and on a lot of these homework questions, I think there's like a thing that you can prompt for hints or look at an example problem. It may not be on this first one, but on a lot of these questions, there is something like that.
Okay, thank you so much.
Yeah, no problem. Have a good one.
You too.